create or destroy energy. You can only transfer it from one form to another. So today, we're going to go through the next, there's actually 2 PowerPoints. So I'm going to try to go through these pretty quickly so we can get to the assignment, because the assignment's not too bad. Actually, the next assignment is a little bit more difficult. So let's go ahead and pull these up. Sorry, I should have had them already up.
I'm good.
Come on, waste some time. Got to teach bell to bell. Come on.
Oh, that sucks. You can't do it now.
Hey, I got it. Oh, but I went too far. Hold on.
Oh, no.
That one. All right. And we want 9.3, both in 9.3s. Open that. Come on. Why is it double tap so hard here? There we go. I got that. Oh. Did I get both or just one? I think I just got one. Oh, let me just come back here and do it.
Not worth how you see.
All right.
I'm trying
We want concepts first and then calculations. All right. So, I'm going to make some notes on the board as we go through this, but I'm going to try to go through it quickly so you got plenty of time to work on the assignment. What we're starting with today is thermochemical calculations, so heat and chemistry, and you're going to be thinking about the math and starting to do some calculations. Most of the questions don't involve math. Some of them do, so they're starting to kind of ease you into it before we get to Hess's law. So the first PowerPoint we're doing is just on concepts. This is just going to go over the ideas. The next PowerPoint, which we're going to do immediately afterward, is going to go over the math a little bit. So I'm going to go through both of these kind of quickly. The key here is exothermic. Exo means out of. And so when I have something that's exothermic, the heat is going out of my chemical or my beaker or my system is what we called it yesterday. So exothermic is out of, I know, it's a little squeaky. So the heat is leaving my system. Heat leaving the system. Oops. So exothermic is out of and heat is leaving my system. And we have 3 things that heat is leaving the system. So if I'm freezing something, if I'm turning my water into ice, I need to cool it down, right? And so heat is leaving the system. I'm taking heat out of the system. Same thing for condensation. Condensation is a gas to a liquid. So I'm turning my steam into regular water. Steam is really hot. Water is room temperature. And so I need to cool it down and take some of that heat out to get condensation. Same thing with deposition. Deposition is gas directly to a solid. I skipped the liquid phase. But again, thinking of water, steam is hot, ice is cold. In order to go from steam to ice, I have to cool that down a lot and all the heat has to leave. So all 3 of these are exothermic. The heat is leaving out of my system. That's what I'm looking at doing right there. Endothermic is going to be the opposite. Endo means into. So the heat is going into your system, and it's going to be the 3 opposite things. I'm melting, I'm boiling, or I'm subliming. All 3 of these, I'm getting a higher temperature. So melting ice, I go from solid to liquid. The ice is cold, the liquid is not, so I have to heat up the ice to melt it. Same thing with boiling. I go from liquid to gas. The liquid is room temperature. The gas is steam. It's really hot. So to heat up the liquid to really hot steam, I have to put heat in and boil it. And the same thing with sublimation. Sublimation is like dry ice. I might try to get some dry ice for a lab next week or the week after, but we'll see. But sublimation is where I go directly from a solid to a gas. The solid is really, really cold, like ice. The gas is really, really hot, like steam. And so I have to put a lot of heat into it to get it to go from ice into steam. And so those are our 2 setups, endothermic and exothermic. So let me write the endo over here. Endothermic means into. and heat goes into the system. Also, we can add a couple temperature things. If my heat is going out of the system and I'm like taking water and turning it into ice, what is my temperature doing? Temperature is what?
Like going down.
It's going down. So temperature is dropping. Over here, my temperature is rising. So endothermic heat is going in, my temperature is going up. Exothermic heat is going out, my temperature is going down. Now let's take a look and see. Wait, hold on. Did I get that? No, the surroundings. Okay, my bad. So let's see. Because the law of the conservation of energy, the energy lost by the system in an exothermic reaction or change will always equal the energy gained by its surroundings. As the reaction releases energy, an observer will feel the surroundings getting hotter if that is if it's releasing enough energy for you to actually feel that. And the other day we did an exothermic reaction. It was an endothermic reaction because my chemical got hotter, so it took heat in. But last week when we did that reaction, we couldn't feel the room getting hotter around us. We weren't mixing enough chemicals. There wasn't enough heat being released. But if I am doing a large reaction that is exothermic, I should be able to feel that heat of that reaction happening. So in an endothermic reaction, the energy gained by the system will always equal the energy lost by the surroundings. It doesn't matter whether it's endothermic or exothermic. Whatever goes in or comes out has to come from somewhere, and it has to be equaled up. I can't create energy. I can't destroy energy. So if I put 5, trying to think of what our temperature, let's just use degrees. If I get a 5-degree temperature change inside my beaker, I had to take 5 degrees worth of energy from outside my beaker. Doesn't necessarily mean my temperature in my room will drop 5 degrees, but it's the same amount of energy needed. So thermochemical equations include energy gained or lost by the system during a reaction. So their example is they will write out the chemical equation, like we've seen chemical equations all year long, and at the end, they will tack on this delta H, and they'll have delta H equals some number. That number is the actual amount of heat that you gained or lost in the system. If it's positive, you gained heat. If it's negative, you lost the heat. Does that make sense? So they're going to start to show you that, and they'll give you an example in just a second. So here's your example. 4 irons plus 3 oxygens goes to iron oxide. My iron is rusting. That's what's happening here. So the heat of this reaction is negative 1625 kilojoules. So the negative tells me it's exothermic because I have my heat is leaving out of the system. So negative is exothermic, positive is going to be endothermic because of which direction my heat is going. And how much did I lose? 1625 kilojoules. This is the actual amount of heat that we're using. Joules is the unit. Kilo means it's a big unit. It's thousands of joules. So we have 1,625,000 joules. And that's the amount of heat that we're using. So coefficients in Ball's thermonuclear equations represent number of moles. Enthalpy of a reaction is directly related to the number of the moles. 3 times the number of moles releases 3 times the amount of energy. So what they're saying here, let me go back to this. If I have this equation and it releases this much energy, if I get another equation that looks exactly like this, but everything is 3 times bigger, I have 12 irons, 9 oxygens, and 6 iron oxides at the end. If everything is tripled, then this amount will be tripled. The more substance I have, the more energy I release or take in. So you're going to look for that in a couple problems. They're going to give you a formula, and then they're going to multiply it, and they want to know how much energy has been released. So chemical reactions involve breaking and making chemical bonds. And this is the thing that is the hardest to think about, so I want everybody to really focus right now. To do a chemical reaction, I start with one set of chemicals, and I end up with a new set of chemicals, right? What happens in between that is first, I have to break the bonds of the old chemicals and get them basically down to individual elements. All of them are by themselves, and there is no like chemical formulas or compounds. It's just individual elements. So that's the way we think of it. Before I can make new chemicals, I have to break apart all the old ones. And then once I break apart all the old ones, then I can make the new chemical bonds in their place and start to form my new chemicals. With energy, this requires a little bit of energy. Both of these, breaking the old bonds and making the new ones, is going to require energy. So bonds in reactants are broken, the new bonds are formed in your products, and there's a certain amount of energy that has to be made or lost in each of those. And I want you to think of it, it doesn't really work both ways, but think of it like a stick. If I have a stick here, and I want to break this stick, do I put energy into it or take energy out of it? I put energy into it. I either like force it to bend and break, I like hit it real hard and try to snap it. But some way, the only way to break this stick is to put energy into it, put work into it, and try to break it. The same thing as with chemical bonds. In order to break a bond, I must put energy into that bond, and it has to be absorbed. That's how it's broken. The opposite happens when I form new bonds. So if I put energy in to break the bonds, when I form new bonds, energy is released. And basically the idea is whether a reaction is endothermic or exothermic is, am I releasing more than I'm absorbing, or is it the other way around? I'm absorbing more than I'm releasing. That's going to determine whether I'm endothermic or exothermic. So just know that for every reaction, energy is both absorbed and released. It's going to happen both times on every single reaction. The only difference is which is more. If I'm absorbing more, I'm going to be endothermic because I'm taking heat in. If I'm releasing more energy, I'm going to be exothermic because I'm releasing some out. And so they have examples for how these look. And I will draw this on the board in a second. They actually have a better thing. Here it is, right here. So for exothermic, what's going to happen? I start with my initial chemicals, and the first thing I need to do is break those bonds, right? So I have to put energy into my chemical in order to break those bonds. So my energy level is going to go up when I break the bonds. Now I have a certain amount of energy for all my individual elements, and I have to put them together to form a new chemical. When I put them together, I release some energy. And for exothermic reactions, what they're showing you, the energy I absorbed is smaller than the energy I released. Can everybody see that? So I'm releasing more energy right here, top to bottom, than I put in at the beginning. So at the start of the equation, my energy level was here. At the end of the equation, my energy level is lower. So from start to end, I went down. Does everybody see that? The general trend from start to end, I went down. My energy went down. That means I'm exothermic. And so what I'm looking for is the chart that's this shape, that overall goes down from left to right. That's going to be the exothermic chart. The opposite is going to be for endothermic. I start out a certain amount. I break those bonds, so I have to put energy in to break the bonds. I make my new elements. And then when I form my new bonds, I only release a little bit of energy. And so this one goes up from start to finish. My energy is increasing. This is endothermic because the energy is coming in. Does everybody kind of see this? So this is going to be your chart. Instead of the study sheet, you should be able to look up here and kind of get your bearings. Exothermic, out of, my temperature is dropping because I'm losing heat. And here on the graph, my graph is going to go down from start to finish because I lost heat. Endothermic is the opposite. Heat is going into the system, my temperature is going up, and I can see in my chart that I'm gaining energy from start to finish. That's because my energy level is coming up. It's endothermic. So we have those two opposite kind of directions that we're going here. So that's the exothermic one. Here's the endothermic one. You can see again, our energy is going up. We put more into breaking the bonds than we get out of making our new ones. And so we are putting energy in overall as a total. Now, let's go to this second one where we actually look at the math.
Well, can we do the assignment
On the second one.
No, because you're not going to listen to me. And essentially, I'll just have to answer every single question as we go through it. How about this? I'll turn the lights on, and I'll make some loud noises so everybody wakes up.
Wow, I need it. You got air horn?
Wake up. Wait. We got chemistry coming in. Okay. Okay. So, endothermic versus exothermic calculations. Now we're going to look at the math, and this isn't going to be too long. There's not a lot we can do here. Basically, what you want to do is treat each of these equations, like chemical equations, as an actual math equation. And you're going to do simple math stuff with them. So what we're trying to do is figure out how much energy is absorbed or released. And one of the things we need to look at is the bond energy, the amount of energy necessary to break a bond. Basically, on bond energies, you will have to look these up on a chart. You're not going to be able to just figure them out. They're going to have a long list of all the different bonds between all the different chemicals. You got to go in and find them and say, well, how much energy am I going to have to take to break this chemical apart? And how much energy am I going to need to make my new chemical? And then you just do a quick formula where you're subtracting. I take the amount of energy I need for my reactants to break those apart. I subtract the amount of energy I'm going to get from my products. And if the answer is positive, then I'm endothermic. I'm adding heat to my system. If the answer is negative, I'm exothermic. Heat is leaving from my system. So simple math equation. All you're doing is subtracting reactants minus your products. So step one, determine the number of moles of each type of bond on the reactant side. Step two, look up the average bond energies for those bonds and multiply the number of moles by that bond energy. Step three, do your little sum, find your totals, and figure out, are you endothermic or exothermic by subtracting. So here's your example. Using the average bond energies, calculate the amount of energy absorbed or released when 2 moles of hydrogen gas form with 1 mole of oxygen gas to form 2 moles of water vapor. Here's our formula. So let me rewrite this so we can kind of take a look at it. Let's see. I need a marker. So we got 2 hydrogens plus 1 oxygen goes to 2 waters. Right? Yeah. And what we need to do here is we need to look up 3 actually, no, we don't need to look these up. I think hydrogen and oxygen, these numbers are going to be 0 because it doesn't really take very much energy to break apart 2 oxygens. They're not really bonded together. I think it's going to be the same thing with hydrogen. We'll see. So really the only energies I'm looking for is what kind of energy does it take to form my new bonds in my H2O. And so they're going to tell me to look these up. I got 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water. So we look up the average bond energies, and actually I was wrong. There is a little bit of energy here for breaking these apart. So we look up the hydrogen-hydrogen bond. They give me a little bit of energy here. We look up the oxygen-oxygen bond. They give me an energy there. I need to add these together. So 870 plus 495. Actually, I need 2 of the hydrogens. So I double that up, plus 495, and I get 1840. The numbers they're going to get from a chart. They didn't show you the chart, but they looked them up from a long list on the chart. In the assignment, there will be a little link to the chart in the question. You just click on it, find your chemicals on the list. We'll take a look at it when we actually get to it. Let me answer this. Hello? Hello? Yes. All right, no problem. Engage. You go see Mr. Stone real quick. Okay, let's see. Let's keep going. So number 4, we need to subtract the bond energies of the products from the bond energies of the reactants. So we added up our bond energies of the products, which is 1840. The reactants is 1365, and then we subtract that, and we get negative 475, which tells us this is exothermic, because I'm losing heat at the end. I have heat leaving my system. That's going to be exothermic. Let's see. What is this next one? Oh, so like here's your list here. So some chemicals are going to have zero amount of heat needed to break apart that chemical or to form that chemical. Other chemicals are going to need some amount. So not everything is going to be a straight up number. You could have a zero. You just treat it like a zero. If it's a zero, it doesn't require any energy to break these apart or put them back together. It just is what it is. Let's see. Basically the same problem, step 1, step 2, step 3. They give us this. Here's your chemical equation. I have CH4, 2 Cl2s, a CCl4, and a 2H2. Basically what you're going to do, you find each of these on the list. They made you a short little list here. I know that the CH4 needs 74.6 amounts of joules, kilojoules, to actually make or break that chemical. Same thing with the Cl2, but that has a 0, so I don't need to factor that in. My CCl4 is a negative 139. My H2 also has a 0 here. So these two really aren't going to come into play. What I'm looking at is breaking this chemical apart and putting that one together. So what's going to happen here, we have only 1 moles of each of these. So 1 mole of CH4. Yeah, we got 2 moles of Cl2, but that's a 0. It's not going to come into play. And we have 1 mole of this CCl4. So I'm going to have 1 moles of each of these. And then as we do this, the only issue is one of these, the number's going to have to be flipped, I believe, into a positive. Or no, if you just subtract them, I guess it ends up as a positive. What do they do here? Let's see. Yep, negative minus a negative is going to be adding together. You still end up with a negative answer, but this is your exothermic reaction. So they got their numbers from the chart. They added up the 2 on the reactant side. They added up the 2 on the product side. And then they did products minus reactants, and they got their answer, which is what we're going to do. So I think, yes, that's the last one. Go ahead and open up the assignment, and we'll take a look at what some of these problems are, and I'll show you an example. Maybe. I feel like most of them y'all are going to be able to get on your own. Oh, I guess it doesn't sign. You can scroll down into chapter 9 and find it if you want, but I'll sign it right now. Let's see. Update this.
Or to be safe.
59. And I will make this tomorrow. Actually, I'll make it Friday for the people there. Okay. If you reload the page, it's assigned now. Okay, so go ahead and open it up, start working. I'll point out when you get to number 4 and they give you this chart right here, they want you to make this chart look like one of the ones that I drew here. So you got to move the different points where the chart matches either the exothermic or the endothermic chart. Let's see. What else? They give you another one. Number 6. That's easy. Okay. Nah. Endothermic, exothermic. Losing heat, gaining heat. Okay, so number 8 is the one where they really ask you to look up the things on the chart. So if you get to number 8, let me know. And I'll kind of give you a walkthrough on number 8. Number 1, let's see. Number 1, endothermic versus exothermic. The easy way to do this is think about, is it putting off heat or is it taking in heat? If it's putting off heat, it should feel hot to you. If it's taking in heat, it's going to feel the opposite. So which of these puts off heat? Which of these is taking in heat? I'll point out, boiling a liquid, where's the heat going? Is it going into the liquid or out of the liquid? Well, but more importantly, I'm boiling it, so what am I doing? I'm putting heat into it. The stove puts heat into the liquid. And so that's going to be endothermic.
Burning candles, exothermic, right?
Yeah, because I mean, I got to light the candle, but once it's lit, I'm not putting any more energy into it. There's only energy being released.
Same with the rocket fuel because.
Oh, I got it wrong.
So burning candle, yeah, anything that's burning is going to be exothermic. If it's on fire, it's exothermic. It's releasing heat. Are you putting heat into the popcorn or taking it out?
I don't know. I'm speaking. Mine was right.
Let me see.
The reaction inside.
There should be two in there.
Here.
I got it.
A heat pad. What's it doing? Where's the heat? Is the heat going in or out?
Oh,
No. A heat pad. It's a heat pad. No. Think about it. What they're talking about? They're talking about like the hot hands they sell at Walmart, where you break the little pack, you stick it in your pocket. Those kind of heat pads.
Wow.
All right, so I'm gonna pause this until y'all have questions. Resume this.
I could not get it.
What number?
3.
Number 3. Oh my gosh, number 3. So let's see. I'm on freeze for some reason. Okay, number 3. Endothermic versus exothermic. So you should know that energy is released or absorbed, right? Endothermic, exothermic, energy is released, energy is absorbed. I have written on the board, flows into or out of the system. So exothermic, I'm flowing out of the system into the surroundings. It's in the top right corner there. Endothermic, I'm flowing out of the surroundings into the system. So those should be there. Heat flows out of the surroundings has to be endo, and heat flows out of the system has to be exo. So it looks like for each of these, there's 2 opposite things. Surroundings are going to increase in temperature. So that is exothermic because heat's flowing out of my system into my surroundings. So my surroundings should get hotter. So surroundings increase in temperature is exo. Surroundings decrease in temperature has to be endo. And then the last 2, products have lower potential energy than reactants, or reactants have lower potential energy than products. That's these charts here. Your potential energy is the flat line at the beginning or the end. So for endothermic, my products have more potential energy because that line is higher. For exo, my reactants have more potential energy. So let's see. All right. So reactants have lower potential energy, should be endo. Products have lower potential energy, that should be exo. And then energy is released as exo, energy is absorbed as endo. What's the problem? What's the problem? What's the problem? Think about it. Think about it. Think about it. Let's see. I'll take a look. Let's see. All right, so let's take a look at number 12. Because number 12, you got to do a little bit of work. There's a chart here. Do you have the same problem as me? MgCl2, H2O, MgO, and 2CHCl. You got a different problem? It's all right. You can do this. We can do this together. So what I'm going to do here, first off, what you need to do to solve this problem, hit the hint button and click on this link here where it says found here. It's going to open up your chart. And so I need to write down my formula. Is the bell about to ring?
Yes.
It's okay. MgCl2, H2O. Marker. Plus MgO plus HCl. Let's see. MgCl2 plus H2O goes to MgO plus H2HCl. Okay. Nice. Then we go to the chart here. Already got one up. And we just need to find our chemicals. Y'all can go ahead and go. I'm going to make this on the video, and it's going to be on the video. So if you want to solve this later, it will be up here.
Ethan, your wallet. Don't forget it.
Okay, y'all get your stuff and go. I'm making a video. So what we have here, we have MgCl2. Let's see, I'm going to scroll all the way down. MgCl2. What I have here is a delta H. Let me make sure I'm delta H. Delta H is the first column, so we're good there. MgCl2 is a negative 641.3, which I will write down. Negative 641.3 plus H2O. I think H2O is going to be a 0. No, it's not a 0. H2O liquid is negative 285.8.
Zam, Mr. Baby.
Hey, be quiet. I'm doing a video. Oh, I forgot. Negative 285.8. Yeah.
Oh, there's only like 5 fingers. Oh, you're junior?
Hey, listen. Be quiet. I'm doing a video. MgO. Where's my MgO? Let's see. Negative 601.6. Negative 601.6 plus 2 HCl's. Hello. Come on in. 2 HCl's. Negative 92.3, but I got 2 of those. So negative 92.3 is negative 184.6. Nice. So then, once you have your formula, you've looked up all of your values, you're going to complete this by adding together your reactants and your products, and then you're going to do products minus reactants. So when I add these together, I get negative 927.1. Is that right? 927.1. I apologize if that's wrong. 6, 7, 8, 9, 27.1. I think that's right. All right. And then add these together. So I got 785.86.2. So negative 786.2, negative 927.1. And then I do products minus reactants. So I have negative 786.2 minus a negative 927.1. Minus a negative becomes plus. And so this is going to be what? Positive. Might as well use my calculator so I don't screw it up. Negative 786.2. Oh, I didn't even have it on. Minus negative 972.1 is 185.9, which tells us, because it's a positive number, that tells us it's exothermic. And no, it's endothermic. I'm sorry. Because the positive number, that tells us endothermic. And the answer for this particular problem should be 185.9. Let's see if we got it right. Let's just see. 185.9. Hold on. Literally almost done. What?
Where'd you get 927.1 from?
Added these two together. No, wait. 927.1 added those two together.
Those two?
Yeah. Yeah. Well, got it wrong. Let's see.
Wait, why did you?
Hold on, what is this? Reaction equals products minus reactants, right? Yeah. So why am I wrong here?
The one shit around.
Maybe, but not. Probably not.
What does the 25 Celsius have to do?
That's them just telling you that the water's going to be liquid. It's not ice or steam. It doesn't really factor into anything. So I don't know. Let me see real quick, and then we'll do the assignment. Okay, so I went and checked the answer, and this is actually the correct answer. For whatever reason, Sapling has what I think is the wrong answer in there. So if you do this problem and get an answer on yours, and you think that it's correct, but Sapling tells you it's wrong, let me know in class. I'll take a look at it, or come in during activity period, and we'll get you fixed up. So that should get you through the assignment today. If you have questions, please let me know, and I will help you out. Thank you.